Select the major product of the following reaction. So we are starting with a substituted benzene, and we are treating this with nitric acid and sulfuric acid. So the first thing we need to do is we need to recognize that this combination of reagents is the conditions for an electrophilic aromatic substitution where you replace one of the hydrogens in the ring with a nitro group. So this is a nitration. So what happens when you mix your nitric acid and your sulfuric acid is you generate an NO2 plus that can be added to the benzene ring. So we're going to take a look at the mechanism for generating that electrophile, that NO2 plus. So we have nitric acid. So here is a general structure of nitric acid. And sulfuric acid is actually a stronger acid than nitric acid, so it's able to protonate that nitric acid. So when you mix this with sulfuric acid, we can protonate the nitric acid. And what we want to do is we want to protonate where we have the OH, because we're setting this up to be a water molecule as a leaving group. So this is going to get protonated by that sulfuric acid. So you'll be generating this protonated nitric acid. And so these electrons can come in to form a double bond and push off that water so that you're getting this NO2 plus, which is a really good electrophile for the EAS reaction. So that's how we're going to be adding the nitro group to the ring. And then the question is, we already have a substituent on the ring, so where does this substituent direct the incoming electrophile? And so we'd want to recognize the pattern that we have here. We've got a pi bond to an electronegative atom in conjugation with the ring, so we can have this withdrawing effect. So this is an electron withdrawing group. This is a meta director. So that means that the incoming electrophile is going to be added to the meta position. So meta is 1, 3. So here is the benzene ring. So we could draw our nitro group here, or we could just have easily drawn it at the other meta position, and we'd want to recognize that those are the same thing. So that looks like answer C. Okay, and we can quickly draw the rest of this mechanism. We've gone ahead and drawn the NO2 plus. So we can have our benzoic acid attack this really good electrophile. And I'm going to show the attack to have the substitution occur at that meta position. So we can just have this pi bond attack the nitrogen, and then we will break one of those NO bonds. It could, the bottom one, it could just as easily have been on the top. And so we're going to get to a carbocation intermediate. So we've added our nitro group here. So we have the positive charge, and we have a hydrogen, and we have the NO2 group that we've added. And so then we just need to get rid of this hydrogen. So we've generated water here. We can go ahead and use water as a base to pull off the hydrogen. Make sure you're taking the hydrogen that is at the same carbon where you've added your electrophile. And then you're going to push these electrons in to re-aromatize the ring. And so one other thing I want to point out, when you look at this carbocation, if you were to draw all of the resonance structures, so you can push this over, and so you'd have a positive charge here. And then you push this down, you have a positive charge here. And what you're going to be avoiding is putting the positive charge directly adjacent to the electron withdrawing group, because that would be a really high energy intermediate. So that's part of the explanation as to why these electron withdrawing groups are meta directors.